Okay, so welcome back to Particle Physics and the Standard Model. This is lecture 37, and last time we saw some real consequences of breaking electroweak symmetry, right. We got one of the most important things that came out of this, which is the acquisition of masses for the gauge bosons, and we derived the masses of the gauge bosons, we got the Z mass, the W mass, and very importantly we also got the photon mass, right. We identified this particular combination of the W3 and the B mu as the photon and saw that it indeed got a 0 mass, and we have convinced ourselves that SU2 cross U1 did break down to electromagnetism. In that process we also identified a relation between the charge, the electric charge and the hypercharge and the third component of isospin, right. And yet another thing we learnt was the Higgs mechanism itself, which is that the 3 Goldstone bosons that we created during the symmetry breaking did not go anywhere, they just reincarnated themselves as the longitudinal degrees of freedom of the gauge bosons, which is exactly what we call masses of the gauge bosons, right. The Goldstones were eaten as the longitudinal degrees of freedom, right. That is indeed the Higgs mechanism. And then we wrote down now after symmetry breaking the couplings that you get between the Z boson and the photon with the fermions, correct. So, we got QED for free just like that by breaking electroweak symmetry, but then we also got the neutral currents associated with the Z boson, okay. And finally, we identified this piece which we wrote down as a fluctuation around the vacuum expectation value. That little piece H was indeed what we call the Higgs boson itself, okay. The Higgs boson that made all the news when it was discovered, and it is still making a lot of news, correct. So, the Higgs boson comes as not a Goldstone. To distinguish it from a Goldstone, people also call it the radial mode. The name should be self explanatory, correct. It is called the radial mode because you write it as a fluctuation around the Higgs wave itself, right, and not a transverse mode, which is what the Goldstones are, okay. And we saw that the mass of the Higgs boson, when you write down the potential for just the Higgs, depends on this quartic coupling, which we have no idea about. Well, now we do, but before the Higgs was discovered people had no idea about it. It was a free parameter, and that is one main reason why it took people so long, okay. The Higgs boson was proposed in 1964 actually by Peter Higgs, but then it took people until 2012 to discover it, just because we did not know what the lambda was. So, you have to search all over the place, and it literally turned out in the last place that people looked at the Large Hadron Collider, okay. A very intricate signature that the Higgs boson has, very unique set of branching ratios to many different final states. So, all of this made life hard, but ultimately it was discovered and the Standard Model was indeed shown to be triumphant, okay. So, that is the story. Now we can go on to how this Higgs boson interacts with fermions and what consequences that has for particle physics, okay. So, masses given by electroweak symmetry breaking, the fermion sector. We already saw the gauge sector, now we are going to go to the fermion sector. So, where could the masses come from? Literally it should come from the Yukawa couplings, right. Remember we wrote the Yukawa couplings between the fermion states, the Quidel and the Higgs boson, the Higgs, sorry, not the Higgs boson, the Higgs field, right, the Higgs doublet. So, that is literally what would give rise to fermion masses also, okay. And you can imagine how it would look like, right. it should look like, for every fermion I can write a mass, and again in 2 spinner notation I have a mass that looks like this. Oh sorry, no dagger here, correct. But it is not just we have every time you have a H there is a V, right. So, it always comes in combinations of V plus H, right, in the Higgs doublet, correct, something here and so on, right. So, this would also give rise to a Yukawa sector for now the Higgs boson, not the Higgs doublet, that would look like this. Agreed, every time I have a H I have a V outside, right. So, I can literally write down the coupling of the Higgs itself, which should look like this. Okay. Now, it is not this trivial, something else has happened here. Okay. So, we should hold on for a second and see what really we have done to get this Lagrangian. Okay. What we did was we diagonalized, okay, the Yukawa matrices. In Flavour space, okay, to get these diagonal masses. So, let us see what I mean by this. Let us go back to the Yukawa sector that we wrote down all those lectures ago. Remember this, in red I have written the indices I j, right. So, there was not one single Yukawa coupling, accounting for all the flavors I had for each of these terms I had 9 Yukawa couplings, correct, including the cross terms. So, there are 9 Yukawa couplings here, 9 here and 9 here, right, in 3 different places, right. To go from here, remember the I and the j need not be equal, but explicitly I have written I and j equal here, I and I and I, right. So, to do this I have, what have I done? I have actually diagonalized the Yukawa matrices. So, in other words, I have taken terms like these, okay, after symmetry breaking I had terms like these, right, E, L, I with the dagger and then E, R, J, agreed. This is what I get after symmetry breaking, right, and then I also have a V sitting out in front, correct, from the Yukawa coupling, from the Yukawa term, right. So, to get the mass I had to go to a basis where I am going to write in shorthand notation a tilde to indicate that that is a column matrix. Okay. So, what is ME? That is not a mass, it is a mass matrix actually. Okay. So, by any MF now I am going to mean a diagonal matrix with the 3 fermion masses, okay, corresponding to the 3 generations. Okay. So, this is a column matrix, that is a square matrix of course, and this is another column matrix. A column in what? In Flavour space. Okay. That should be clear now, right. So, similarly I have secretly diagonalized another Yukawa which is for the up quark, right. So, I have this. So, let me just write these things down quickly. This got diagonalized to yet another diagonal mass matrix, and this also for the down quark got diagonalized. Okay. Okay. So, there is an important consequence of this diagonalization. Okay. Let me again, for the sake of clarity, let me just explicitly write down what the each of these tildes mean. It just means in flavor space I have F1 LR, F2 LR and F3 LR. What are F1, F2 and F3? The three generations, like up charm on top, down strange and bottom, electron muon tauon and so on. Okay. So, what does it mean to have diagonalized the matrices? It means, right, I used some unitary matrix to take the Y E matrix. I had to rotate the Y E matrix in one direction with some unitary matrix, and yet another unitary matrix rotated in another direction in order to get the diagonals, correct. Remember this from linear algebra? That is how I diagonalize matrices, right. So, these two are unitary matrices that did this for me. Okay. Similarly, I got the diagonal U. How should I have got it? There must have been some unitary matrix that I hit the YU matrix with on one side for the left handed fields, right. Basically this column, right, the UL tilde column, I should have rotated it with some LU dagger, right, and similarly the UR column matrix I rotate with some R, basically that is where the notation comes from, L and R. Okay. And similarly for the D. Okay. Good. Now, that implicitly, okay, already tells us that we can measure these fields in two different bases, right, two bases, plural of basis is bases. Okay. One is the Yukawa basis, also I can call this the interaction basis. Here it means interaction with the Higgs, okay, and the other is mass basis. Agreed? I have written fields. We started out with fields that look like this, that is the Yukawa basis, then we went to the mass basis, correct. Now, that has a very interesting consequence, okay, if you consider interactions with the W bosons. Okay. Why is that? Because to get the diagonalizations, we had to make use of both the left and right handed fields, right. The mass terms only are possible when you marry left and right handed fields. We keep saying this, right, to get Lorentz invariance. And then in flavor space I was able to diagonalize by using rotations in both left handed fields and right handed fields. But the W bosons interact only with left handed fields, right. So, something funny is going to happen now. Okay. Let us look at the W boson interactions, okay, in the flavor basis. So, W boson interactions. So, in the flavor basis, what do I have? This is how I would write the kinetic terms. Agreed? Sorry, not the kinetic terms, the interaction terms. Okay. So, it comes through the kinetic term through the covariant derivative, but these are literally how the interactions go. I have dLi, would you agree? Although I have not written it down before, this is exactly what you should expect, right? From the Z, for the neutral currents, we had currents that looked like, you took the vector current and the vector minus axial current here, right. So, I should expect to use only vector minus axial current here because I use only left handed fields, right. So, in two spinner notation, I can write the interactions this way. So, to get the charges right, I have to put a plus there and I get W minus mu U L I. Agreed? Okay. Now, if I go to the mass basis, okay, what happens now? I have to rotate all these matrices, right, using these rotation relations, right. In that case, I am going to use, maybe I will use a different color to indicate mass basis, okay, because I am going to use the same notation, but a different color means mass basis, okay. So, U L I, okay. What else do I have? Let me switch color. When I write only for the fields, I am going to use green color, okay. And I have this, I still have dLi, but this is in the mass basis, remember that, okay. But it is not just dLi actually, right. Why is that? Because for the rotations, I have to hit it with some LU dagger, right. That is what we did here when we went to the mass basis, right, this LU dagger. So, that is what I am writing here, and over here I just have LD, correct. And now, since I am multiplying both these matrices, I have an IJ, right. It is the product of this, which is the matrix I have to consider when I sandwich it within the fields. Agreed? So, that is the first term. The second term is again in the mass basis, I am going to write with a green color dLi, okay. So, ULJ now, yes, and what is the matrix here? It is LD dagger LU IJ, and I have sigma bar mu W minus mu, okay. That is what it is in the mass basis, okay. Clearly this is different, right. So, clearly we picked out another matrix here, right, or clearly we picked out new terms here in the coupling, right. So, if you measure these things in the mass basis, the couplings would basically look, will be different from the interaction basis. So, there is a physical difference here, it is a physically observable effect just from the fact that you need to diagonalize the Yukawa terms in flavor space after symmetry breaking. Yes. So, now we can define this matrix LU dagger LD, okay. I am going to define that as the CKM matrix, okay. So, very important matrix in particle physics, in flavor physics, and we can now expand this matrix. This is the usual notation for what the elements are. The notation should be self explanatory. This is what I have when I want to, VUD is the coupling that I can pull outside when I hit what? A down quark with an up quark, right, or an up quark with a down quark. If it is an up quark with a, oh, I wrote something wrong here, this is a B. If it is an up quark with the B quark, then that is what this is, right. So, all of this is in flavor space. Okay. So, this is an important consequence of symmetry breaking. CKM stands for Kabibo, Kobayashi and Maskawa, and these two folks got the 2008 Nobel Prize for realizing the consequence, this consequence, and working out further consequences of this. Okay. So, Kabibo is an Italian, and Italians are not happy that Kabibo did not get it. The reason is Kabibo in the beginning proposed the existence of this matrix for 2 generations before the 3rd generation was found. Okay. So, the Kobayashi and Maskawa, after the 3rd generation was found, proposed the full matrix, which had other interesting consequences, and they got the Nobel Prize. Okay. Now, since LU is unitary and LD is unitary, it follows that CKM matrix is also unitary, right. So, this is the first property one should remember about the CKM matrix is that it is unitary. Okay. And testing its unitarity is a whole industry in experimental physics. Okay. It is a very important test of all this, okay, of all these theories. So, let us now see how many really independent parameters are there in the CKM matrix. Okay. So, right now it seems like I have written 9 parameters, but not really. Okay. Physically, there are much fewer than 9 independent parameters that you can actually observe from the CKM matrix. Okay. So, let us see how. So, because it is unitary, how many real degrees of freedom are there? There are 9, right. It is n squared, right, for an SU, for a UN unitary matrix, for an n by n unitary matrix, right. How do I know that? So, you start out with 2n square, right. So, let me just write it, remind you again, you start with 2n square. Why 2? Because generically it is a complex matrix, right, but then it goes to n squared from the condition u dagger u equals 1. So, you get half the constraints are removed, basically half the degrees of freedom are removed, you get n square constraints basically, right. So, okay. So, that is why you start with 9 real degrees of freedom. Okay. But what are these degrees of freedom? Are they all rotation matrices? It can't be, right. Even in SO3 when you have a 3 by 3, okay, in SO3 that is fine, but not all the degrees of freedom in an SO3 are rotation matrices, correct, or sorry, in an SU3, not all the 9 degrees of freedom can be rotation matrices, right. So, how do we actually count what are the rotation matrices, what are the rotation angles, sorry, I kept saying matrices, what are the rotation angles and what are other parameters, okay. So, here is how you do it, if the CKM matrix, right, were real, yes, that would have been an O3 matrix, right, an orthogonal matrix basically, a 3 by 3 orthogonal matrix. In that case, we know that there are 3 rotation angles. Okay. So, since I have 9 real degrees of freedom and since it is a complex matrix, right, what could be the other 6? If 3 are rotation angles, what could be the other 6? It means VCKM has 6 complex faces, okay, because 3 are rotation angles, okay, but not yet. This is not the complete picture yet, okay. At this moment, this would be your preliminary senses of the, by senses I mean, you know, SCENSUS, not SCNSES, preliminary senses of the degrees of freedom, okay. But you still want to ask what are the physical degrees of freedom that you can actually observe, okay. So, for that we have to consider, let us take the masses again, okay. I can write the masses this way, correct, dLi dRi. So, I am using Einstein convention. Where repeated indices are summed over. Okay. Now, notice that I can always reface the fields this way. Okay. So, I am going to write some of this down and then wrap up this lecture. We will take up the physical meaning of this in the next lecture. Okay. So, I can always make the following refacings where I reface the left handed fields and then if I reface the right handed fields by the exact same face. Okay. Would you agree that this term is unchanged under this? These two faces eat each other, correct? And similarly, if I reface the up type quarks by yet another face, okay, but the left and the right handed ones I am going to reface by the exact same face. Now, would you agree that similarly this combination will leave this mass term invariant? That tells me that I have a freedom in refacing all the fields, okay, from the mass. The mass terms allow me this freedom. In other words, there is a built in, let me write this in a different color. There is a built in U1 power 6 chiral symmetry. Why chiral? Again, the left and the right handed ones can act independently in this case, and why 6? Because there are 6 flavors, right? Okay. So, I am going to wrap up here and say that we are going to make use of this freedom to basically rotate away the complex phases that we have in the CKM matrix, but then it turns out that you cannot radiate away all the 6 phases. It seems like we have 6 rotations that we can do, because it is a u1 power 6, there are 6 phases, but you will still be stuck with one phase, and we will see how that happens, and that phase turns out to be super important for the standard model. Alright. So, I will stop here. In the next class we will take up this calculation. Thank you.